The aim of today's lecture is to deal with the shortest path problems. We're gonna study about graphs, the corresponding weights associated to all the edges in these graphs. Then we're gonna talk about the heuristics, and finally, we're gonna deal with the algorithms in order to solve the shortest path problems. Well, first of all, we need to make the difference between shortest path strategies versus the pathfinding algorithms, right? Well, the main difference is that in shortest path problems, you have a starting graph like this here at the bottom, like this, where you will find very well defined all the edges that connect all the nodes in the graph, right? That's the main idea. The shortest path problem has several options, several paths to follow. As you can see here, from A, you can go to B, or you can go to C, right? So the main idea is that in shortest path problems, you have already the edges to follow, right? So you're expected to decide which edge should you take for the next step, where you want to go from a starting point, let's say A, and a target node, let's say F, D, E, whatever. But on the other hand, we have the pathfinding algorithms. Here, in the pathfinding algorithms, you have the origin, the start node, and here you have the target, right? But you don't have the edges. You have like a layout with, for example, here you have 3 obstacles, as you can see here, right? And you're expected to define the trajectory to be followed from the starting node A to the edge node B, right? So the main difference between the shortest path methods and the pathfinding algorithms is that in the shortest path, you have the edges, you have all the possibilities well defined in the graph, while here in the pathfinding, you don't have the edges. You should, if you have here, for example, the origin and here the target, you should decide all along the layout what is the path to be followed, right? So you don't have here the edges well defined. You have all the possible positions, and you should decide how to define the path properly, right? That's the main idea. Obviously, we have like a simplification of these pathfinding algorithms when you turn these maps into a grid-based search. When you have like a layout, and let's say that here is, for example, the origin, and this is the target, right? Well, here you can define like several nodes, several possible positions, several waypoints from the origin to the target here in the layout, and then the problem of the pathfinding is simplified, and you turn a pathfinding problem into a shortest path algorithm, shortest path method, right? Well, the pathfinding, as you can see here, is strictly, well, is directly connected with the motion planning of mobile robots. That's why here, in this part of the course, we're gonna deal with mobile robots. We're gonna deal with a real mobile robot application in our lab. Well, what about here in our problems, where we want to find the optimum path to be followed? We must define first the edge costs. So how much is it when you go from some node to its neighbor, right? That's the idea. You have an associated weight that puts into numbers how much it costs to go from A to B, being A and B neighbors, because they are connected by an edge, right? So these are what we call weights. As you can see here, this is the weight from A to B, because this is a unidirectional graph. You can go from A to B, but you cannot go back from B to A. But here at the bottom of the figure, you can see that here we have a bidirectional graph. You can go from A to B, but you can do it the other way, the way back. So from B to A. And here I make the difference because you are not forced to have the same cost to go from A to B that from B to A. And here you have a simple explanation. Let's say that here you have A and here you have B. This is the ground level, right? So this is level 0 meters above the sea, right? So here you have 0 meters, right? And then the cost of going from A to B, despite the length, the distance is the same. For example, the fuel consumption is greater, is bigger when you go from A to B than from B to A. That's why, for example, the weight to go from A to B, this weight will be higher, will be a higher value than the weight from B to A, right? So that's the idea. The effort that you must do from A to B is higher than the effort to go from B to A. So that connects with the meaning of these weights. The weights cannot be simply the distance. Can be, for example, the distance weighted by the power consumption, weighted by the mean speed that you can have in this road. For example, if we consider that this is a village and this is the neighbor village, and you have several roads that connect A and B, right? So they have different distances, but also they can have, for example, maximum speeds, right? So these weights are not strictly the distance, but they can be the distance weighted by something else or directly something else that put into numbers how much it costs to go from one node to the neighbors. Well, so this can be gathered, this information about the weights can be gathered all together within the adjacency matrix or list, right? As you can see here, we have a directed graph. As you can see, is unidirectional because you have all the edges that have a single direction, right? But it's a directed graph. Let's say that here, for example, we consider number one, node number one. Node number one, as you can see, is connected to two different neighbors, right? It's number two with a total cost of 1. And 1 is also connected with node number 3 with a total cost of 5, right? So if we need to gather this information within a single matrix, this adjacency matrix, we will say the following. Here we have the origins, and here we have the different destinations or targets, right? So the origin node, the final node. So node number 1 is connected to 2, connected with 2 and 3, right? With a cost, as you can see here, connect 1 is connected to 2 and 3 with the corresponding weights that are 1 and 5, as you can see here. Node number 2 is connected only, as you can see here, with node number 3, total weight of 3. That's why here we have a 3. And then node number 3 is connected with node number 4, as you can see here, with a total weight of 2. And node number 4 has no connection with other nodes. Despite you may think that node 4 is connected with 3, that's not true. Is 3 connected to 4, right? Because you can go from 3 to 4, but you cannot do the other way around. Right. Let's say now that here we make the difference with this first directed graph just by reversing this arrow in here, this edge, and now 4 is connected to 3, but 3 has no connections. As you can see here, the only difference is that 3 has no connections with other nodes, but 4 now is connected with 3 with a total weight of 2. Well, the nodes that have no connection with their neighbors, right, here are symbolized by here the star, right? So the symbol, this star, is equivalent to 0 in the matrix diagonal and equal to infinity outside the diagonal. What do I mean with this? The total cost to go from 1 to 1 is 0. That's why here the values are 0 in the matrix diagonal. 0 and 0 here, 0 and 0. Because the total cost that put into numbers to go from 4 as the origin and 4 as the destination is 0, right? Then the other stars here outside the diagonal of this matrix are infinity. Why? Because you cannot go, the total cost of going from 2 to 1, is infinity. The weight is the highest value as possible, right? Well, let's have a look at an example here. You can stop the video and check that the matrix corresponds to these numbers in here, to these elements in here, according to this original graph. Well, remember here, as the rows, you have the origins, and here you have the destinations or targets. So let's check, for example, number 3. Number 3 means this row, right? Here you are, 1, 2, and 3. As you can see here, we have 5 nodes. That's why here 1, 2, 3, 4, and 5. And let's have a look at number 3. 3 is connected to node number 2. Can you see here with a weight of 1? That's why here we have on the second column for the third row a number 1. Then here connected to node number 4 with a total weight of 3. That's why here we have a 3. And finally, it's connected to node number 5 with a total weight of 5. So that's why here we have the 5 as the cost of going from 3 to 5. Obviously, the diagonal, the cost of going from 3 to 3 is 0, right? And then we have no connection from 3 to 1. That's why here I have an infinite number, right? Well, you can discuss with me about the meaning of these zeros in the diagonal. What I mean? What do I mean? Well, is the following, is that to stay here, if you stay with, for example, the engine of your car just on, right, it has a cost of going from 2 to 2, I know, but this is not a state machine, right? This is not a transition diagram for a state machine, right? So we will not consider the coast that supposes to stay in a specific node, right? The important thing is that here we want to go from an origin to a target, right? So to remain within a single node has no sense for us, right? That's the idea for at this moment, right? Obviously, if we have like a conflict between two mobile robots and they must take the same route, for example, let's say that here we have two mobile robots that must, for example, here, we have one mobile robot coming from here, the other one coming here, and we have a conflict because they both must go through this route, right? So let's suppose that here I have a mobile robot going there, another mobile robot in here going there, and we have a conflict, right? Because who's the first to go to take this edge? Well, it will depend, for example, on priority, right? So the level of emergency for the corresponding task of any of these two robots, right? And the other robot will stay here just waiting for the other one to take this path. Only in these cases, I would consider some values in here to stay, right, in a specific node, right? But this is not our problem in this subject, right? We are only planning the routes for a single mobile robot. Well, so in order to define, to calculate the optimum path, the optimum means the path with the minimum cost, the minimum total cost of going from the origin to the target, right? We have a handful of algorithms, right? We have uninformed methods. These are what we call the blind or brute force methods, right? And we have the informed methods. Now I will make the difference and I will explain every of these specific methods, right? All of these 5 methods. Well, the uninformed methods are the typical methods, for example, when you enter here a maze, right? And you want to get out of this maze, right? That's the visual image of this kind of algorithms. You don't have weights. So in these methods, we don't have weights, right? So these are the brute force methods that will assess all all the possible paths to follow, right? And then we will take the minimum cost path as a result of the application of this algorithm, right? And we have 2 different algorithms, the breadth first search and the depth first search. I will explain, I will make the difference between them, right, in the following slide. And then, on the other hand, we have the informed methods. These are the methods that use weights in all the connections between the candidate nodes, right? This will be the greedy algorithm, the Dijkstra's algorithm, and finally, the A star algorithm. This, you will see, will be the optimum, the most efficient algorithm that we gonna deal with in today's lecture, right? Well, I need to make the reference that all the codes that I'm going to use here belong to this researcher, right? And well, I ask for his permission, right, in order to use all the corresponding codes in my presentation and during my lectures, right? Well, let's have a look a simple example in order to calculate the adjacency matrix, right? Because afterwards, we're gonna deal with the breadth versus the depth first search algorithms. Remember that these are the blind algorithms, the algorithms that they don't have weights assigned to the edges, right? But just before, let's remember only this, how to calculate this adjacency matrix in here. As you can see, let's say that we want to go from A to E, right? As you can see here, we have several connections. This is a single directed graph, so it's a unidirectional graph. We don't have bidirections in here. So A is connected to the neighbors B, C, and D, as you can see here. So that's why A connected to B has a weight of 2, A connected to C, a weight of 8, A connected to D, a weight of 5, and because we have no connection with E, we have an infinite. I put this example in order to make you be noticed about here, despite you have like an indirected connection between A and E, here you don't have an 11 number in here, because you will see here I have a connection AC, and C is connected to E. So if we add 8 and 3, here I have a connection between A and E. That's not true. A is strictly not connected to E, right? That's the thing I want you to be noticed about, right? That A and E are not connected, because A and E are not neighbors. One node is neighbor to another node if they have a path that connects directly both nodes, right? So there is no intermediate node between them, right? Well, you can stop the video and check the remaining elements of the matrix, right? But let's now use a breadth versus a depth first search. So now I have, like, in a similar appearance like this, but it's not the same example. Here I have several nodes, as you can see. I have A, B, C, D, E, and F, right? So because both methods are what we call blind methods or brute force methods, they will assess all the possibilities in our diagram, right? And the difference is only about how they assess all the possible routes to be followed. What do I mean? The following is that breadth, as you can see here, breadth is the following. We start here at the top of this graph, right? So A is connected to B and C. Can you see here? So the breadth marked here in yellow, right? At the following level, so because I start here, the following level is all the neighbors of A, right? So this method will assess the connection between A and B, and then A and C. That's why we use the adjective, well, breadth, right? That's the name. The breadth first search. We use the breadth possibilities in here. So we assess all the possibilities for every level in the diagram. So we assess A and B, A and C, right? Because we have to assess all these nodes. So the nodes to be assessed will be A, B, C. A, B, C. Then we have D, E, and F. Why? Because we will assess all the nodes in here, all the neighbors of B, because we have a single neighbor, we have a D in here, and then when we have assessed all the neighbors of this node in here, we go to the following node in the previous level, obviously here, the C, and we assess E and F, right? So let's say, for example, that here we have a node called, I don't know, R, right? We have a node called R, right? So this R should be here between the D and the E. Here the R. Why? Because we are using the breadth first search algorithm. That means that for every element in a level, I will assess all the neighbors at the following level. So that's why A, which are the neighbors of A, B and C, so B and C. Then what about the neighbors of B? DR, DR, and then I switch to C and I assess all the neighbors of C. That's why we use the breadth first search. So this is a typical queue data structure, right? Because we consider that the following level is the queue for the previous level. That's the main idea. But then we have, on the other hand, we have the depth first search. The depth means the following: to go to the depth of the diagram. So that means that we start with A, then we go to the first neighbor of A is B, then instead of checking C, that means the breadth for search, we will assess D in here, right? So that's why here we have the difference, ABC for the breadth, and for the depth, ABD, because we reach the last branch of this kind of tree. So you must figure that A is at the bottom of the tree, right? Is the root of the tree, and then you have like all the possibilities in here, right? So what do I mean? The breadth means that for every neighbor, you assess all the neighbors. Then for every element in this level, you assess all the neighbors, right? And go on. This is the breadth. But the depth means to start from the root and go to the end. Start again from the root, and then from the root, sorry, and then go to the end. And then this, and then this. This is the depth first search. That's why here we have ABD, ACE, that's why ABD. Then because we repeat A, we go to C, that's why here I have a C, then E, and then F, right? But U, for the depth, the image is the following: this, and then this, like going from the root to the end of every branch, right? And this, the image of this, is a typical stack for a data structure. Remember, this kind of pin with all the bills stacked in here, right? Well, let's have a look at the previous example, remember, but now we will consider both approaches, the breadth and the depth first search, right? We will not consider the weights, right? Because these algorithms are uninformed algorithms. So that means that we will not use the information about the weights between the nodes, right? So what about the breadth first search? The breadth first search will do the following. We start in A and we want to finish at E, right? That's the idea. So we start from A. The breadth means that it will consider all the neighbors at the following level, right? So that's why I have A, B, A, C, and A, D, right? So the list will be A, B, C, D of the nodes, right? And then the last node will be E. Why? Because B has as a neighbor C that has been taken into account just before, and then E is the neighbor of C, and at the same time is the neighbor of D, right? So the important thing is that the breadth first search is an uninformed algorithm that starts with the root, with the starting node, and then assesses all the neighbors at the following level, and then all the neighbors at the following level, and so on, right? On the other hand, the depth first search will be the following, will be A, B, then we will consider B, all the neighbors of B, the first neighbor is, and the only neighbor is C, so the list will be A, B, C, and then E. When you reach the end, you go to the following one, and then to the following one. So the list will be A, B, C, E, as you can see here, A, B, C, E, and then A, C, E, C is assessed, well, it is already in the list, and finally A, D, E, the last element is D, because this is the unvisited node, right? So these methods at the end, they assess all the possibilities that we have here in the diagram, right? But the methodology here is different from the depth first search. Well, so just because now we're going to use the informed methods, so the methods that will use the costs of going from one node to the neighbors, right? We first start with the heuristics. We're going to use the following. Well, the heuristics at the end is like the rule of thumb. It's like to use your knowledge about the system, about the graph. What do I mean? The following. Well, as you can see here, we have A, and let's consider that E is the target. So E will be the target, so the ending node, and A will be the origin, right? So the heuristics is like a consideration on how far are you from the target node. You will see. Let's say D, for example. D is this far from the target node. What do I mean with this far? Here, I have a distance of 1.5 and 1.5, as you can see here. So if we add this length in here, we have a total distance of 3. So the heuristics, so like a rule of thumb consideration on how much it costs of going from D to E is 3. So if you could fly, so if this is a road, but you could fly, if you could go directly from D to E, you had a total cost of 3. That's, for example, if you live in Terrassa, for example, and you want to know how much it costs to go from Terrassa to Barcelona, right? You know that both cities have a distance between them about 20 kilometers, right? 20, 25 kilometers. So that's like a heuristics. It's like an estimation of how much it costs of going when going from Terrassa to Barcelona. That's the idea. And the best consideration of heuristics should be, well, heuristics should be an under consideration on the real cost. What do I mean with this? As you can see here, the distance from D to E, the distance is 3, as you can see here. That's the value of the heuristics, right? But then for the real value of the cost when going from D to E is 1, right? This is an undesired situation because the real cost is higher than the heuristics, right? But this has an explanation. Remember when we were talking about some kind of a slope in the terrain? Here we have D, and here we have E, right? The distance, if you could fly, if this is an airplane and you could fly from D to E, the Euclidean distance from D to E is 3, right? But because here you are going down, right? Maybe the effective cost is so low, right? So the explanation about this could be like this, this explanation, right? This situation in here, right? When you save energy because you are going down this slope, right? But well, the main idea of the about the heuristics is like this. Heuristics is like an estimation about how much it costs of going from the actual node to the target node. As you can see here, from A to E, the heuristics of A is 6. Why 6? Because as you can see here, I have these rectangles. Can you see? This rectangle in here, this rectangle in here, this rectangle in here, and in here, right? This side is 2.5 long. This side is 1.5 long. And if you apply the square root of the addition of the squared value of 2.5 plus the squared value of 1.5, you have these 3. So this edge, not the real weight, I'm talking about the heuristics, the estimation, if you could fly, right? So that's the heuristic cost of going from A to C to E. So that's why you have a 6, right? And this 6, as you can see, is strictly an under consideration about the real cost, because here we have an 8 and here we have a 3, so it's 11. So this 6 is an under consideration, right? So in order to keep things clear, the heuristics is a consideration, it's like a rule of thumb on how much it costs when going from the actual node for every node in the diagram to the target, right? And this consideration should be smaller than the real cost of going from the actual node to the target, right? This way, the methodology that we're going to use in a close future will be optimal, right? That's the main idea. And as you can see here, the heuristics of the target, when you're going to go to the target, is obviously 0, right? Well, so let's now apply these heuristics on the greedy algorithm. This is the faster and the most aggressive algorithm, right? In order to reach the optimum path when going from the origin to the target, right? So let's consider that we want to go from A, that's the origin, and our target is E, right? This is our target. So we will assess, first of all the neighbors. So the method, the greedy algorithm, consists of the following paths. We will, following steps, sorry. We will consider all the neighbors of the actual node. We are here, right? We are on A. So let's consider that we are here, right? On A. And we assess all the neighbors. Let's say B, C, and D, right? Well, we have B with a heuristic value. B is 5, right? Because the heuristics of B is 5. Can you see here? 2 times 2.5, right? So this heuristics will be 5. Then for C is this, 3. So we have a 3 in here. This is the heuristics of C. And the heuristics of D is also 3, right? Because we have here a 3. So we have a tie, right? We have a tie because you can go either to C or D because they both have the minimum heuristic value for the neighbors of A, right? Then let's consider, for example, C, right? Now we are here. Consider that we are here. So let's check all the neighbors of C. C has only a single neighbor and is the target. So the optimal path will be A, C, and E, right? So the waypoints will be A, C, E, this path, with a total cost of 11. Can you see here, right? With a total cost of 11, because the real cost is 8 plus 3, as you can see here. But as you can figure out, we have other paths that they have a smaller cost. Let's check here. As you can see, if you go A, B, C, E, you have 2 plus 4, 6, plus 3, 9. So this is not the optimum path, right? The greedy algorithm is very fast, but the results are poor, right? And obviously, if you check here, we have another path that is A to D is only 5, and then D to E is only 1. So total cost 6. It's close to half the value of the cost of the result of the greedy algorithm, right? So the message is greedy algorithm, very fast, but most of the times it's not optimal. So the cost will not be the minimum as possible, right? In the following slides, I will show you two different methods, the Dijkstra algorithm, that will give you the optimum path, right? Will give you the optimum value. So we'll give you back the minimum cost as possible, but the computational efficiency of the Dijkstra algorithm is not good, right? So we will make like a relaxation of the problem, like a simplification of the problem by means of the A star algorithm. That's like a mixture between the greedy and the Dijkstra algorithms, right? So well, let's go now to the Dijkstra algorithm. As I told you, the Dijkstra algorithm will give you the minimum cost as possible. And I told you that in this simple example is only 6. A, D, E, right? Well, afterwards, I'm going to show you how this Dijkstra algorithm works, right? But the important thing is that the Dijkstra algorithm will reconsider all the unvisited nodes in order to find the optimum path, in order to ensure that you will be given the optimum path with the minimum cost as possible, right? How it works? Let's check it step by step, right? We will start here. This is the origin, and this is the target, right? Well, first of all, you are here, so you can draw that you are here, right? I know that I'm in A, and I have three candidates, three neighbors. I can go from A to B, A to C, A to D, right? With a real cost, here we are not using the heuristics. The Dijkstra algorithm is not using the heuristics at all, right? The algorithm is using the real cost when going from one node to the neighbors of this node, right? So here we have a 2, 8, and 5. So I write here 2, small 2, 8, and 5. So my candidates are B, C, D. That's why here I use a dark green and a light green in here. These are the candidates. And I will decide about, so my choice will be the smallest value as possible. So here we have A to B, 2. That's why here B turns into dark green, right? So it seems that the optimum path will be A, B, and something else, right? Well, as you may know, this B is not part of the final list of waypoints because the final list of waypoints will be A, D, E, right? So B has nothing to do with D. So let's check what is happening right now. Well, now I'm gonna consider all the neighbors of B, right? So I add the neighbors of B to the candidate list, right? Here, the candidate list was B, C, and D, right? Now the candidate list is C and D because I have decided about B, right? So then I will do the following. I will consider C, but in two different ways. First of all, 8, as you can see here, a small 8. That's the reason of the small 8. And I have here 2 plus 4, 6. Because if you go this way, you can reach C by two different ways. AC, ABC, right? Fine. So now I have three different possibilities. The key point is that the Dijkstra method reconsiders again the already visited nodes, well, not visited, the previous candidate nodes, right? So here I have 6. This is the total cost of going A, B, C, 8, AC, and AD is only 5. So now I will forget about 8 and 6, and I will consider D. So that's why now I visit D with a total cost of 5. You with me? Then I will assess all the neighbors of D. The neighbors of D are only node number E, and it's 5 plus 1, only 6, right? So now I assess again all the previous nodes in the candidate list. I have not forgotten this C, remember? So it's 6 in here, 8 in here, and a 6 in here. As you can see here, I have not considered this path because E is not a neighbor of an already visited node. C is not visited yet, right? I have visited A, B, and D. Can you see here? So that's why here this path is not considered yet, right? Because C has not been considered as a visited node, right? So I have 6, 6, and 8, right? So we have a tie. We have a tie between the 6 and the 6, right? So you must decide between C and E, right? Just because E is a candidate and it's the target itself, we decide about E and the final path will be A, D, and E because E, when you have in front of you a tie and one out of these candidates in the tie is the target, you must go to the target, right? Just because here you don't have a cost of 0, right? So that's why here, despite this is a 6, here you may have a 1, 2, 3, right? That's the idea. Fine. The most important thing, the Dijkstra method, as you have seen, this is a small example, but this is slower than the greedy algorithm. The greedy algorithm is quite fast, right? This is slower. Why? Because this method reconsiders the previous unvisited candidates, right? As you have seen in the example. So that makes this method slower, but that makes this method optimal, right? So that's the idea. You reach at the end the optimum path, right? Well, another important thing is that the Dijkstra algorithm doesn't work with negative weights. As you have seen in all my examples, all the weights in the edges are positive, right? Because I consider that there is an effort, a positive, a waste of energy when going from one node to the neighbor, right? And this will be applied to real applications because this is not a mathematical divertimento, right? Is a real problem. And you will have a mobile robot that is wasting electrical energy from the batteries, right? So the batteries will be discharged. You may run out of battery, right? So that's why I use always positive weights. So forget about the mathematical divertimento that would be if this has negative weights, right? Because you will not save energy in our application in this course, right? In a different course, you may save some energy, like when you are charging the battery, when you're going back a slope, for example, and these kind of things. Well, the lab has a flat floor, right? So we don't have different slopes, so you cannot save energy. Every time the mobile robot moves, every time you waste energy, right? That's the main idea, the main message. Fine, so what about the A star algorithm? As you have seen, this method, the Dijkstra, is quite slow. Just consider, for example, that you want to go from city A to city B, right? If you should consider all the candidate roads to be followed in order to go from A to B, should be a very, very long time running algorithm, right? So a quite long time running algorithm. That's the idea behind the Dijkstra algorithm. Well, I know it's optimal, but if we have like a graph with a lot of possibilities, the running of this algorithm will explode, right? So when you run, for example, Google Maps, you have the best route in a short period of time, right? So if Google Maps used the Dijkstra algorithm, it would take a lot of time, right? So we have like a simplification of the Dijkstra algorithm, and we have the A star algorithm. This method is used in video games, in planning the route when you want to go by means of Google Maps from A to B. And well, at the end, the A-star algorithm is widely used in your future experience, right? Will be widely used in your future experience. So, well, the A-star is a mixture between the Dijkstra and the greedy algorithms, right? So, for example, you could, for example, the Dijkstra plus the greedy, right? The Dijkstra, remember, use the real costs, the greedy use the heuristics, right? And you could use, for example, a lambda value like giving different, this is lambda, right? 1 minus lambda, right? So the complementary value of lambda, lambda is a value from 0 to 1, right? It's like a parameter. You have here 0 and you have here a 1, right? So if lambda, for example, is a 0, you use purely the Dijkstra algorithm. So remember, very slow in the execution, but optimal results, right? If you use a 1, you will use the greedy algorithm. It's not optimal, but it's very, very, very fast. But you can use a mixture, right? Let's say lambda equals to 0.5, half the value of the costs in the Dijkstra algorithm, half the value of the costs of the greedy algorithm. That means the heuristic costs, right? That's the idea. Obviously, you could use like the lambda 0.25, 0.7, whatever you want, right? So here I will explain simply the A star algorithm that takes into account with the same weight, so lambda equal to, let's say, 0.5, right? The Dijkstra weights and the greedy weights, right? That's the idea. So the total cost of when going from one node to the neighbor is not only the real cost, is not only the heuristic code, but also the addition, but well, not also, instead of this, is the addition of the real cost and the heuristic cost. I will show you here. Remember the heuristics here in a small number in green. The heuristics of A is 6 because the cost of going from A to E, that this is the origin and this is the target, right? The cost when going from A to E, following the rule of thumb, is only 6, right? Here we have a 3, remember? This is a 3. Here we have a 5 because this was 2.5, 2.5. These heuristics can be the Euclidean distance or the Manhattan distance. Remember, the Euclidean distance means that you can go from the origin to the target by means of the diagonal values, right? These diagonal paths, right? But if you follow the Manhattan distance, means that you can only use this kind of paths, like going through the streets in a city. Well, so now we're gonna have a look at an example, an application example of shortest path algorithms. We're gonna use the greedy algorithm, and on the other hand, we're gonna use the Dijkstra algorithm. Well, the example is as follows. Here we have the origin, as you can see here, with an O, and then we have the target with a T. And we have the weights, as you can see here. We have the weight when going from the origin to A is 3. Here we have 7, 1, and so on. So these are the real costs when going to when going from one node to its neighbors, right? On the other hand, here we have the heuristics. Here, the heuristics of node n, corresponding to node n. As you can see, the heuristics of the target is 0, obviously. Here, the heuristics when going from O to the target is 15. That means that we suppose that the cost when going this way, if you could fly, this should be a 15, right? Is an under consideration on how much it costs to go from O to T, right? That's the general idea. It's only an estimation. It should be, in order to be optimal, it should be an under consideration, right? So it should be smaller than the cost, the real cost, when going from O to T, right? But as you can see here, for example, if you follow O, D, E, T, we have 7, 8, 10. So this is bigger, right? So this is only an example, right? And we will find the solution according to the two different algorithms. So the important thing is not if these heuristics are strictly right. The important thing is the method to be followed, right? So, well, let's start with the greedy search algorithm, right? Well, here we have the origin, and then we have three candidates, A, F, and D, right? Why? Because they are the neighbors of O. Let's check the heuristics. Remember, we are using the greedy, so forget about these costs, right? So we consider the heuristics of A, D, and F. A is 15, D is 11, and we have F that is 12. So the smallest value is 11, right? So that's why we choose O, D, right? Then, on the other hand, which are the neighbors of D? We have G here, we have F here, and we have E, right? So no connection between D and B. B and D are connected, but D and B, they are not connected. So let's check F, G, and E. F is 12, remember. G is 7, but E is only 6. So we choose E, right? Finally, the neighbors of E are G or the target, right? Because the target is 0, we decide about the target. So as you can see here, we have a very fast method that considers this with a total cost of 10, as you can see here, right? And the list of waypoints is ODET. ODET. Right. So let's now check what's the solution that we can find by means of the Dijkstra algorithm. We start again with O, and the destination, as you can see, is T, the target. First of all, here we have the candidates, the neighbors of O, of the origin. They have a weight of 3, as you can see here. This method, remember, this method has nothing to do with the heuristics. So the heuristics list here is forgotten, right? So, well, the real cost when going from O to A is 3. From O to D, 7. And here we have a 5. What's the minimum value? 3. So we decide about A. Then we assess the neighbors of A, and we have D and B. Because D was the neighbor of O, here we have a 7, remember? But now because D is a neighbor of A, here we have a 4. What's the minimum value of all between all these candidates? Here we have a 5, not bad, 7, 4, and 10. So we have a 4 in here, right? So we decide about O, A, and D, right? Because this 4, we found this 4 thanks to this path, right? So that's why O, A, D. Well, we decide about D, and then we have new candidates. This E as a neighbor of D, right here. Here you have no number because V is not an already visited node. It was only a candidate, remember, with a weight of an associated weight of 10, 3 plus 7, because it's a neighbor of A, right? That's why here I have no weights, right? Fine. So then we are considering this neighbor, 5, 10, 7, 7, and 5. So we have a tie. Just remember the Dijkstra algorithm does not forget about the previous candidates, remember. But here we have a tie. We have 5 and a 5 between these candidates, right? So we decide, for example, about the E, right? But otherwise you could have decided about F, right? Here is only an example, right? Well, I have decided about E, and then here I have the neighbors of E that are G with a total weight of 8, and here with a total weight of 7, right? The target, right? Well, let's check again what is the smallest value. As you can see here, we have a 5, right? So for the next step, between all these values, 5, 7, 7, 8, 10, 7, you should decide about this 5, right? Despite you have reached the T, the target in here, right? So we decide about the F, because this F was only 5. That's what it makes the Dijkstra algorithm so slow. Here you have the T, the target reached, with a total cost of 7, right? But remember that 7 is smaller than 10. Can you see here? So it's better than the greedy algorithm, but the Dijkstra does not stop yet, right? The method wants to find the best route, right? So not a better route, the best. So that's why here we are considering F, right? So then we have 7, 7, 8, 10, 7. So we have a tie here and here, right? So we could decide all along this, well, we could decide about one out of these 3 7s, right? But just because one of these elements in the tie is the target, you should finish the method, just because if the other elements in the tie are not the target, we have for sure a minimum cost of 1 that connect the other nodes in the tie to the target, right? So the optimum path is this, and this, and it's 7. And remember, we have reached before this 7, not in this step, just here, right? But just because here we have a 5, the method slows down the execution, the finding of t, just in order to be sure that this is the optimum value, right? That's why the solution ensures you to find the minimum cost for the resulting path, right? So 7 obviously is smaller than 10, the result of the greedy algorithm. So I encourage you to stop the video and try to do on your own the A star search by using the same weights and the same heuristics than before. And you will find the optimal solution just in a quicker form than the Dijkstra algorithm, right? Because at the end, the addition or like the superposition between the greedy and the Dijkstra algorithms makes the A star method faster than the Dijkstra and similar optimality than the Dijkstra, but in a quicker way. The aim of today's lecture is to deal with some application examples concerning the shortest path algorithms. Well, I have extracted this example here in the screen from the Carleton University in Canada. And well, the aim of this problem, the statement, is that we want to go from this origin in here, from this origin to the target. We have the coasts that are associated to these edges, as you can see here. And then we have also the information about the heuristics. So remember that the heuristics is like a rule of thumb about how much it costs to go directly from some node to the target. So these heuristics, for example, for A, this A in here, this 6, is the consideration of this, the cost of going from A to T, to the target, if you could fly. So it's an under consideration. This 6 is for sure smaller than the real cost that could be 7 and 5 or 12 and 3, right? So, or for example, 2, 4, and 5. So the main idea is that the heuristics is like a lower bound on how much it costs to go directly. So not following the paths, not following the edges, right? The cost of going from the actual node to the target. And these heuristics will be used by two methods that we will see here in this example. The first method is the greedy algorithm, right? The greedy algorithm, remember, we start in the origin, right? And we have some neighbors of this node, right? We will consider these neighbors, but only on heuristics, right? So we will consider A as a neighbor, B as a neighbor, C as a neighbor of O, all of them, right, of the origin, and we will consider A, B, and C, the heuristics that are associated to these nodes. Remember, these heuristics, and these heuristics, right? So, as you can see here in the list, the minimum value is 5. So that's why the next node in the list of waypoints to the target will be B. Then, according to the actual node that is B, let's consider all the neighbors of B. The neighbors are C, E, D, A, as you can see here. And out of them, the minimum value, as you can see here, is D and E. Can you see here? We have a tie. We have the same heuristics associated to D and E, right? So you can consider any of them because we have a tie in here, right? So let's consider, for example, that we take D as the choice, right? Then we consider again the neighbors of D, and because one neighbor of D is T, the target has the minimum value as possible, that is 0, because the cost of going from the target to the target is 0. It has a heuristics of 0, right? So that's why the greedy algorithm results in this list of waypoints O, B, D, and T with a total cost of 14. But what it would happen if we had chosen E instead of D? Then E, and then E has as neighbors here D with heuristics of 3 and the target. So another possibility as a result of the greedy algorithm is O, B, E, not D, E, and T, with a total cost, as you can see here, of 5, 3, 8, 15, right? So any of these two possibilities is the solution when the greedy algorithm is applied. I know when you have a tie, depending on your choice, the total cost and the list of waypoints obviously will change, right? So we can have a total cost of 14 if we choose D, or 15 if we had chosen E instead of D, right? Well, let's have a look now at the Dijkstra algorithm that results in the optimum path, in the optimum cost path, right? But in opposition to the previous method, you will see that it takes a long time to run, right? Here, it's quite easy to apply. It's very fast to apply because you only consider the heuristics, right? And you don't reconsider the previously unvisited nodes, right? Because the heuristics, as soon as you get close to the target, these nodes will be out of the real possibilities of the on the solution, right? Because when you are getting closer and closer to the target, these nodes are far. Because they are far from the target, these nodes, we have no need to reconsider them, right? That's the thing. That's the real characteristic that makes this algorithm so fast. But in opposition to that, we have the Dijkstra algorithm that will result in the optimum solution, but it will take a long time to run. Well, first of all, we have the origin, and we consider all the neighbors, right? So that's why here we have 4, 5, and 2. As you can see here, the heuristics list has disappeared because the Dijkstra algorithm considers the real costs of going from one node to the neighbors, right? So nothing to do about the heuristics. The heuristics is like a relaxing strategy in order to make the algorithms faster and faster, right? So if you use 100% heuristics with the greedy algorithm, the algorithm will be so fast, but the solution will not be optimal, right? If you use strictly the real costs, so if you don't use the heuristics at all, the result will be optimum, but the problem is that it will take a long time to run. Well, here, as you can see, we have 2, 5, and 4 as the real costs of going from the origin to any of its neighbors, right? So we choose obviously 2 because it's the lowest value. So 2 is chosen. Now we again reconsider the previous and visited nodes. You can see here the C, but again, the neighbors of A. So that's why here on B, we have 2 different weights assigned. Why? Because you can reach B by means of directly going from O to B. That's why here we have a 5. But then you have a 2 and a 2 in here. That's why here we result in a 4. Then here we have a 4, remember, because we are reconsidering these 2 neighbors of O, of the origin, despite we have decided to go to A, right? This is not the final decision, our final solution, right? Then we have 2 additional neighbors here, neighbor of A. Remember, we have B and 2 additional D and F, as you can see here, right? We have a tie because here you can see a 4 and here you can see again a 4. So we have a tie, right? We can choose any of them, right? That's why here we have 2 different possibilities, OAB, OC. We decide OAB, right? But we could have chosen OC. So it doesn't matter. Right, again, we repeat about the previous unvisited neighbors. Remember C, it has not been visited yet, right? F, because it's a neighbor of A. D, because it's a neighbor of A, and now a neighbor of B, because we have visited V, the V node. But C, now again, because it's also a neighbor of B, we have here a 5. So if we compare 4, 5, 7, 8, 9, and 14, we can see that 4 is the minimum value. That's why here we visit this C, right? Again, the neighbors, the unvisited ones, and the new appearing neighbors, because E is not only a neighbor of B, but also a neighbor of C. And you can see here 8, 7, 8, 9, and 14. We have no discussion at all. Here the minimum value is 7. So that's why we choose E. As you can see, we have reached E according to O, to the waypoints O, A, B, and E, and we result in a 7, right? Again, the neighbors. Here we have 8 coming from E to D, 8 from B to D, 9, A to D, and 14 here. And also, we have the target as a neighbor because we have visited E, and the target is a neighbor of E, right? But here we don't have a number because this is only a neighbor of A. It's not an already visited node. It's not in green, right? Well, as you can see here, we have a tie. And we decide, for example, to go O, A, B, E, and D. But we could have chosen O, A, B, D, right? Again, the neighbors, 13 in here, 14 in here, 14 in here, right? Obviously, we choose 13 because it's the lowest number. So we end with the solution O, A, B, E, D, and T. But we could have chosen O, A, B, D, and T with the same total cost, but with a different list of waypoints, right? So that's why here I remark the other choice, right? So we have two different lists of waypoints with the same total cost of 13. That obviously is lower than the result with the greedy algorithm. Finally, we will apply the same, we will tackle the same problem, but now we will apply the A-star algorithm. Remember that the A-star algorithm is like a mixture between the greedy algorithm and the Dijkstra algorithm. So that means that we will use 50% each the information about the real cost of going from one node to the neighbors and the heuristics assigned to every single node. So here I have written here in white, as you can see, the list of heuristics assigned to every node. So the origin has a heuristics of 8. Remember, is the underestimation of the cost of going from O to T, then this for C and for E, right? So this is the Euclidean distance. It's like an estimation on the line that connects, remember, the actual node to the target, right? And for optimal results, it should be an underestimation, right? So the heuristics must be lower than the real cost of going from the actual node to the target, right? If this heuristics is higher or equal to the real cost of going from the actual node to the target, the algorithm will result in non-optimal results, right? That's the general idea. Well, without the strict maths behind this algorithm, remember that we will use 50% each the information on the heuristics and the real cost, right? In opposition to the Euclidean distance, so the straight line that connects every single node to the target, being assigned to the heuristics, you could use the Manhattan distances. Remember, the Manhattan distance is like if you move along the street, right? You go along to this street and then this street, and you add the length of this side and the length of this side. Remember, Euclidean distance, the straight line, and the Manhattan distance, orthogonal lines, right? Here, you move to the right, and then you go down for every single node. So these heuristics can be calculated in two different ways, right? Well, let's consider that we have visited the origin, right? And we will consider not only the cost of going from O to all the neighbors. Remember, here I have a 2, 5, and 4, but also the heuristics for every single neighbor in here. Remember that here we have a 6, another 6 in C, and a 5 in B. So you add 2 plus 6 is this 2 plus this 6, right? So this will result in 8. Then here we have a 5 plus 5, so that's why here we have a 10. And 4 plus 6, that will result in 10 in here. We compare 8, 10, and 10, and for sure, we result in, we choose this A. So now we reconsider again the previous neighbors. Remember, here we are, but then we will consider the new neighbors for A. Here you can go to B from A, as you can see, so that's why here we have 2 possibilities. Then here 2 new neighbors have appeared, right? Well, if we apply the same thing, remember, 2 plus 2 is the total cost. Here you have a 4, right? And then here in B, we have the heuristics when going from B to T. As you can see here, this number is the result on the addition of the real cost of going 2 plus 2, 4, but you add only the heuristics of this actual node, right? So the heuristics of A has not been added in here, right? So this is a 5, not an 11, right? Is a very important thing. You add the total cost, 2 plus 2, but you add the heuristics for this neighbor, only for this neighbor, right? Well, the same goes to this, as you can see here, right? It's a 9 because you add 2 plus 7, right? That's why here the real cost is 9. But then you add a 3 because it's the heuristics of D. You don't have a 9, 6 plus 3, right? That's not true. And it's the same reason why you don't have added 8 in here, right? Here, for the calculation of the total cost when going from O to A, it's 2, this cost, plus 6 is the heuristics of A, not the addition of the heuristics of the origin and the A, right? It's not 14, it's only 6. So the same reason for every single node in the diagram, right? Well, if you have a look at all these numbers, we have a 17 in here, far to be the minimum, 12, far to be the minimum. We have a tie in here, 10, as you can see, but 9 is the choice, right? So OAB will be the choice, right? Now, again, the neighbors. So I will not repeat myself. It's always the same, but the difference between the A-star algorithm and the Dijkstra algorithm is that we are using the heuristics, and this will make the algorithm faster, right? Well, now we again reconsider all the neighbors, right? Well, here we have a 4 plus 6 is a 10, right? Here we have another possibility, 11. Here we have a 12, right? Because 2 plus 7 is 9, plus 3, right, is 12. Here we have the same 17 than before, right? Here we have a 10. Why? Because we have an heuristics of 3, and the total cost is 2 plus 2 plus 3. It results in 7, right? But here we have another possibility, right? I have this possibility empty in order to calculate it on real time, in order to understand what am I doing for every node. Here you can see 2 plus 2 plus 4. So for this edge in here, we have an 8, right? And then we are expected to add the heuristics here, that is a 3. 8 plus 3, right? So we have an 11 in here, right? So the choice must be E, because it's the minimum value of the list. 11 here, 10 in here, 12, 11, and 17. But some of you have noticed that here, strictly, we have a tie. We have a 10 in here, but we have also a 10 in here. So you could choose either, right? So we have decided E, but I strongly invite you to decide about C, right, at home, and just resolve the problem, and you will reach the same solution than me, right? But I strongly invite you to do on your own, right? Well, here we have E, and then we reconsider the previous neighbors. Remember, here we have an 11, right? Here we have again an 11, 12, 17, right? And now, out of all these numbers, we will choose this D. I repeat that I'm not considering C, right? Because I invite you to do it on your own, right? I have forgotten this, right? This possibility, right? I have chosen this E. Just try on your own this C, right? Well, so now here I have decided D, and again, for all the neighbors, we have the minimum value here, 11, right? It's closer here to the target. For sure, here we have again an 11, but remember that you are expected to choose C on your own solution, right? So we have 11, and finally the target, right? So this is our choice, O, A, B, E, D, and T, with a total cost of 13, right? Well, according to this explanation, it may seem that the A-star algorithm is not faster than the Dijkstra algorithm, right? But in those applications that we have a huge amount of nodes, right? For example, I want to go to city number 1. This is my origin, and this is my target, city number 2. We have a lot of roads that may connect both cities, right? The A-star algorithm will save some time because this algorithm, the A-star, will consider only all the nodes that they have the minimum value for the heuristics. So the A-star algorithm will go in that direction, right? But if you have a road that is going there and then go back to city number 2, and here you have some nodes, the Dijkstra algorithm will be considering these nodes, right? But these nodes are not on the right direction that we must follow when going from C1 to C2, right? So you will notice this when, for example, using Google Maps, right? Sometimes you ask Google Maps to go from one city to another one, right? From an origin to a target. But sometimes you know some tricky routes that save some time, right? And these tricky routes, it may imply to go just further to the city, to this destination, and then you get some fast route, right? Because you know something that is not in the algorithm that is using Google Maps, right? Google Maps is based more or less on this A-star algorithm. Video games are based more or less in this algorithm, right? Because they save some time, well, a lot of time at the end when calculating a route for this origin to any destination, right? But sometimes you may know just a more efficient route because you know something that the algorithm doesn't know, some extra information, right? So if the information is not collected by the algorithm at the beginning, obviously your route may be faster, right? Or just shorter, right? That's this shorter in time, I mean, right? Right, so now we will see another application example for the shortest path algorithms we have dealt with here in this course. The example is as follows. As you can see, we want to go from this origin in here to this target here at the bottom right of your screen. So we have the heuristics for every single node here in this map, and we will apply the greedy, Dijkstra, and A star algorithms again, right? So remember, the greedy search algorithm. This greedy search will consider only the heuristics. The heuristics has been applied here in green color, right? So we will consider at the first stage all the neighbors of O. So the neighbors are A, C, G, and F, as you can see here. As you can see, G is only 5, C is 7, and then we have 10, 12, 10, so nothing to do with the optimal solution, right? According to this greedy search algorithm. So we will choose G, obviously. Then we have the target as the single neighbor, as you can see here. So we have no competition of neighbors. So the target, that obviously is the only and one minimum, well, the one and only node with the minimum heuristic value, right? So the total cost is 10 plus 4, 14, right? So the root will be OGT and the total cost will be 14. What do we expect? So that the Dijkstra algorithm and the A-star algorithm will result in a lower value for this total cost, right? Well, so let's now go to the Dijkstra search algorithm. We consider now the real costs, remember, so the heuristics, nothing to do with them, right? So here we have a 3, 4, 5, and 10, right? As you can see here, as I told you before, these nodes A and F are on the wrong direction to T. T is in that direction, right? So as you can see here, 3 and 4 are the minimum cost. As you can see here, we have a 5 and a 10, right? But they are on the wrong direction of the target, right? To the target. Well, so now we consider obviously the minimum value, that is 3. So we will consider again the previously unvisited neighbors. Here we have the 4, the 5, the 10 in here, right? But now we add this neighbor in here, this B, and this D, that is 15, right? Well, we have a tie. Here we have a 4, and here we have a 4. So we have a tie. We decide, for example, F, right? I strongly invite you to choose V at the beginning, right? And just try to solve on your own the same problem according to the Dijkstra search algorithm, right? Well, so we consider F, and then because we consider F, it appears this new route OFG with a total cost of 12, right? Well, so according to all of this, we have this possibility because it's the minimum value, right? Then, according to all the neighbors, the previously unvisited nodes that are neighbors to these visited nodes, apart from that, it appears this 8 associated to E, right? We calculate the minimum value, and as you can see, is this 5 in here, right? Well, it appears new neighbors, as you can see here. Here we have, remember, this 15 in here, because it's the addition of 3, and then this 12 in here, right? So we have a 15, and here we have an 8, right? As you can see here, because we have, for this 8, the total cost when going from the O to A, B, and then E, right? It's 3 plus 1 plus 4, it's 8, right? But here, as you can see, I have left empty this connection in here because I want to calculate it in order to show you how I calculate every cost for every node. Here we have a 5 from O to C, right? Here we have this 5, and then we add this 6, so we have an 11 in here, right? Well, so according to all these nodes, right, it's clearly this 8, the minimum value, right? Well, according to the new neighbor is this 8 plus 3 is this 11, right? We have this tie in here, these two 10s. We have a tie in here, two 11s, 12 and 15. So nothing to do with this, nothing to do with this, but we have a tie here. So that's why I have chosen this unvisited node, right? It appears a new neighbor is the target, right? But the total cost is still so high in comparison to this tie in here, right? So we consider now the node number D, right? Well, named D. And again, I reconsider the previous neighbors. Here you have a 14, right? But the new neighbor that is also T, but now the total cost is 13, right? So the final choice is O, A, B, E, D, and T, because the total cost is smaller than 14, right? So it's the minimum as possible. As you have seen, the Dijkstra search has visited all the nodes in the diagram, right? While, on the other hand, we had the greedy search that is very fast in comparison with the total cost of only an additional unit, right? Well, let's go now to the A* search algorithm. We start again with the origin to this target, but now we will use the heuristics as the additional information in order to calculate the total effort to go to one node to any of its neighbors, right? So, well, here, remember, I have these 3 plus the 12 because is the heuristics associated to this node A, right? Then here we have the 13, 3 plus 10, because B is only 10 about the heuristics. Here, for C is 12, just because 5 is the real cost, but then we have the heuristics that is 7, right? So the minimum value, as you can see here, is 12, right? as a difference from the Dijkstra algorithm, as you can see here, this node and these nodes are not considered at the first stage. Why? Just because these heuristics and these heuristics both have increased the final value, as you can see here, the final cost of going from O to A or from O to F, right? So that's how we, at the first stage, we have saved these nodes. They have not been assessed at the first stage because they are far to be on the direction from the origin to the target. So that's the tricky question of the A-star algorithm, right? And that connects with this mention, this example I told you when going from one city to another city by means of the Google Maps algorithm, right? Well, right, so now, because we consider, remember this C, it appears a new neighbor, it's D, right? And to G, you can go from O to G or O, C, G, right? Here we have a tie, right? But here you have a 14. So according to this 13, 15, and 14, we are expected to decide the minimum value. And now, not at the first stage, but at the second stage, we need to reconsider F, right? Because the total cost, the real plus the heuristics, is the minimum as possible at this stage, right? Again, we reconsider all the neighbors, right? And the new neighbor here, G, is also a neighbor of F, right? And we will assess the minimum value for all the costs. Remember 15 in here, we have a tie, again, 16, and we will choose 14 because it's the minimum as possible, right? Again, we reconsider all the neighbors, right? But as you can see here, we have still a 15. We have here still 15s, then here a 16, and then as you can see here, the total cost is 13 plus 0 equals to 13. Why? Because here we have 5, 6, 11, then we have 13, because here we have a 2, and the heuristics of t, because it's the target, is 0, right? So we have chosen O, C, D, and T with a total cost of 13, and as you have, and as you can see here in this slide, nodes B and E, they have not been assessed, right? In comparison to the Dijkstra algorithm. And A, right, has not been visited yet, and G has not been visited yet. So the A-star algorithm has saved a lot of time in front of the Dijkstra algorithm, but with the same result, right? It may happen in the future that you may find an example that the A-star search algorithm, right, will not result in the same minimum as possible value than the Dijkstra algorithm. So sometimes it may happen that the Dijkstra algorithm will result in a lower value, in a lower total cost than the A-star algorithm. This may happen just because the A-star algorithm saves some time and it's not assessing all the possibilities, right? That's the crux of the problem, right? You have the A-star that saves some computational time, but the toll that you must pay for that is that it may not result in the optimum solution.